Containers. Think of containerization, or simply containers, as the standardized shipping container of the digital world. In the physical world, before we had standardized metal shipping containers, moving goods was a chaotic mess. If you wanted to send a crate of spices from one side of the world to the other, workers had to manually load it onto a cart, then a train, then a ship, and finally another truck. Each step required different tools, and there was a high risk that the goods would be damaged or lost because they didn't fit the transportation method. Standardized shipping containers changed everything. Now, the goods are packed into a metal box that is the exact same size everywhere. The crane at the dock doesn't need to know what's inside the box. It just needs to know how to grab the box. Whether it's on a ship, a train, or a truck, the box fits perfectly. Software containers do exactly the same thing for your applications. They take the code, the libraries, the configuration files, and the dependencies and lock them inside a digital box. This ensures the application runs exactly the same way on your laptop as it does on a massive server in a government data center. As you prepare for your certifications and look toward a career in cybersecurity, understanding containers is no longer optional. It is how modern, scalable, and secure applications are built and deployed. Part 1: Containers versus Virtual Machines. The most important concept to master for your technical exams is the difference between a virtual machine, VM, and a container. While they both offer isolation, they operate at completely different levels of the system. Imagine you are building an apartment complex. A virtual machine is like building a completely separate house for every resident. Each house has its own foundation, its own plumbing, its own electrical system, and its own roof. In the digital world, this means every VM includes a full copy of an operating system, the guest OS. It also has virtualized hardware like a virtual CPU and virtual RAM. Because each VM is carrying an entire operating system, they are heavy. They take up gigabytes of space and can take minutes to boot up because you have to start that whole OS every time. A container, on the other hand, is like an apartment building. All the residents share the same foundation, the same plumbing, and the same roof, but they have their own private rooms. In the digital world, containers share the host operating system's kernel, the foundation. Because they don't have to carry their own operating system, they are lightweight. They are often only a few megabytes in size, and they can start up in a fraction of a second. Part 2: The engine and the image. To work with containers, you need to understand two key terms: the image and the engine. First, let's talk about the image. Think of the image as the blueprint or the recipe for your container. It is a read-only file that contains everything the application needs to run. If you are a cybersecurity professional and you want to run a specific network scanning tool, you find or build an image of that tool. The image never changes. It is the static source of truth. Second, we have the engine. This is the software that takes the image and runs it, turning it into a living, breathing container. While there are many engines out there, Docker is the industry standard you will encounter 99% of the time. The engine sits on top of your host operating system and manages the apartment building. It ensures that container A cannot see the files in container B and that neither of them can interfere with the host system. Part 3: The cybersecurity advantage of microservices. One of the biggest reasons the cybersecurity world loves containers is the shift toward microservices. In the old days, applications were monolithic. You had one giant server running the web interface, the database, and the user accounts. If a hacker managed to find a flaw in the web interface, they were in. They had access to the whole server and everything on it. With containerization, we break that giant application into dozens of small microservices, each running in its own isolated container. The web server is in one container. The database is in a second container. The user authentication is in a third container. From a defensive standpoint, this is a fortress. If a hacker compromises the web server container, They are trapped inside that specific digital box. They cannot see the database because it's in a separate container with its own isolated network. This attack surface reduction makes it significantly harder for a breach to spread across an entire organization. Part 4: Portability and the clean slate. As a technician, you've likely heard the phrase, "But it worked on my machine." This is the nightmare of software deployment. You write code on your Ubuntu machine, but when you move it to a Windows server, it crashes because a specific library is a different version. Containers solve this forever through portability. Because the image includes every single dependency the code needs, it is completely self-contained. It doesn't matter if the host server is running Ubuntu, Red Hat, or Windows Server. As long as the Docker engine is there, the container will run exactly the same. Furthermore, containers offer a clean slate. In a cybersecurity lab, you might want to run a dirty script that changes system settings. If you run it in a container and it messes everything up, you don't spend hours fixing it. You just kill the container and start a new one from the original image. In half a second, you are back to a perfect, clean state. Part 5: Orchestration and Kubernetes. Managing 1 or 2 containers is easy, but imagine you are a massive government agency like the POD or a global company like Google. You might be running millions of containers at the same time across thousands of servers worldwide. You cannot manage that by hand. You need a captain for your fleet. This is called container orchestration. Kubernetes, often called K8s, is the industry standard orchestrator. It is the brain that manages the fleet of containers. It handles 3 critical tasks. Auto-scaling. If your website suddenly gets 1 million visitors, Kubernetes sees the stress and automatically starts up 100 more containers to handle the traffic. When the crowd leaves, it shuts them down to save money. Self-healing. If a container crashes or dies, Kubernetes notices within milliseconds. It kills the dead container and starts a brand new one to replace it, ensuring the application never goes offline. Load balancing. Kubernetes acts like a traffic cop, making sure that incoming requests are spread out evenly among all the available containers so that no single server gets overwhelmed. Summary for the professional technician. To wrap this up for your technical studies and your career, remember these core principles. Containers are lightweight. They share the host's operating system kernel, making them much faster and smaller than virtual machines. The image is the blueprint. It is a read-only file that contains the code and all its dependencies, ensuring it runs the same way everywhere. Docker is the engine. It is the most common tool used to build and run these containers on your local hardware. Kubernetes is the orchestrator. It manages containers at a massive scale, providing self-healing and auto-scaling. Security is built in. By using microservices and container isolation, you limit the damage a hacker can do if they manage to breach one part of the system.